All right, today we're looking at the general idea behind partial fractions and how they relate to integration. If you're in my calculus class, that means I know you've done partial fractions before in pre-calculus. But if you're watching this video and you're not in my class, you may not have done partial fractions before. The idea is that every rational function usually is the product of two functions on the denominator there. Because we have two functions, or two separate rational functions, that when you combine them, you have to get common denominator. And so the idea of partial fractions is breaking it apart into that common denominator. So we would have something over x plus 3 plus something over x minus 1, and we'll call those numerators a and b. Okay? And so if we were to do common denominator on this side, we would have gotten a times x minus 1 plus b times x plus 3 over x plus 3 times x minus 1 equals 7x plus 13 over x plus 3 times x minus 1. So we're breaking it apart into this, and we're getting this part right here, this product after we get, or this final part after we get common denominator. Now, we don't really care about the denominator. We know they're common. We care more about the numerators here. We want to find out what a and b are so we can have it as these separate fractions. To find out what a and b are, we're going to just take the numerators and set them equal. Because if we did our common denominator correctly, this numerator must equal 7x plus 13. And at this point, we need to try and figure out some x values that we know would give us equal numerators. Now, here's the thing. We have a couple we can already pick. We know that if we plug in x equals 1, honestly, any x value, these two numerators should equal. And if we plug in x equals negative 3, because once again, any x value, these two numerators should equal. Now, why specifically these two? Well, if we plug in x equals 1, this is going to turn to 0, eliminating one of the variables we want to solve for. And if we plug in x equals negative 3, this is going to turn to 0, eliminating one of the variables we wanted to solve for. So we're going to do two separate equations. One where we plug in x equals 1, so 7 plus 13 equals 0a plus 4b. And then we solve, so that's 20 equals 4b, b equals 5. And then we do one with negative 3. Plug in negative 3, we get 0. That one becomes, we get negative 21 plus 13 equals a times negative 3 minus 1 gives us negative 4 plus 0b. So the b is going to cancel out. We get, what is that going to be? 7, 8, negative 8 equals negative 4a. So a equals 2. So now we have a and b, and we have our decomposed fractions. We have 2 over x plus 3 plus 5 over x minus 1. And if we go ahead and try and combine them, get common denominator, we end up back with that 7x plus 13. Now, why does this help us in calculus? Because if we tried to integrate this first one here, we couldn't do it. But now that we have two separate fractions, that integration becomes much easier. So here are common partial fraction decompositions. If you have two binomials that are multiplied together, it's a over x plus 2 plus b over x plus 3. Order doesn't matter there, just x, the first one, a over the first one, and b over the next one. If you have a binomial squared, this one's a little weird because you have to think what two fractions would have needed to get common denominator. A lot of things my students, or a lot of issue my students first make, is they try and say it's x plus 5 and x plus 5. Well, it's not going to be that, because if you look at these, they already have common denominator. That's not going to be what we're looking for. The only way we could end up with x plus 5 squared and have gotten common denominator is if one of them was x plus 5 and one of them was already x plus 5 squared. And so you have a over b, and b there. And the next one is when you have a binomial that's, or a polynomial, let's put a polynomial, that's a bigger power. So we have a over x plus 3, that part's the same, but we should always have our numerator to be 1 degree less. So this should be bx plus c over x squared plus 5. Got to make a slightly more complex numerator for that one, and then we can solve it that way. And these are what we do. Now, the big thing for this one, now for the first one and the last one, you're still going to be cross multiplying to get common denominator. But for this one, if you wanted to set up your getting common denominator, and we wanted to get common denominator here, this fraction with the b wouldn't have to have multiplied by anything to get common denominator. The only one that needed something is the a. So it's a times x plus 5 plus b over x plus 5 squared. So that's your combination there when you actually combine it to get that numerator that we're looking for. Now let's actually apply this to an integration problem. We have this one right here. We have x plus 5 over 2x plus 3 squared. If we tried u substitution, it wouldn't work. It's not one of our inverse trig ones. It can't be split up and worked for us. That's not gonna help us. So our best option is to do partial fraction decomposition. Okay, so let's do some partial fraction decomposition. If we do that, we end up with, split this up, we got a over 2x plus 3 plus b over 2x plus 3 squared. And now we want to try and get the common denominator, and really we just need the numerators, so we want x plus 5 to equal a times 2x plus 3, because we need a common denominator, plus, well, b doesn't need anything to get a common denominator, so it's by itself. All right, and this one's going to be a little bit different from the very first one we did, because we know what we need to plug in to get rid of the a. If we plug in negative 3 over 2, that a is going to completely go away. So we get negative 3 over 2 plus 5 equals, that's 0, b. So that gives us 7 over 2 equals b, which is great. But there's nothing that's going to cancel out the b. So we need another x. And now at this point, since we can just plug in b, we can pick any x we want. So I'm going to look at this and I'm going to say, I think 0 looks like a really good x. Things will go away there. So we end up with 5 equals 3a plus 7 over 2b. Or sorry, not 7 over 2, just 7 over 2. b is 7 over 2. We'd subtract the 7 over 2, so that gives us 3 over 2 equals 3a. Divide by 3, so 1 over 2 equals a. Now the big thing is make sure you plug your a and b back into the correct spots. It's going to change your answer if you don't do that. But now what we have, and because these are constants, we can just pull them out. We have 1 over 2 times the integral of 1 over 2x plus 3 dx plus 7 over 2 times the integral of 1 over 2x plus 3 squared dx. And now we can just use u substitution. Technically, they're both going to use the same u, so we can just apply the same u to both of them. U equals 2x plus 3, du equals 2 dx. We need a 2 on the inside, 1/2 on the outside, so this becomes a 1/4 integral 1 over u du plus a 7/4 integral u to the negative 2 du. Integral of 1 over u is natural log absolute value of u. 2x plus 3. 7 over 4. Integral of u to the negative 2 is u to the negative 1 over negative 1, so we'll change this to a minus. 7 over 4 times 1 over 2x plus 3, and then plus c. And there's our final answer. All right, it doesn't change very much from here. Once again, the x's you're picking are trying to cancel out a's, b's, and c's if you can. If you can't, then plug in the variables you do know and maybe make a system of equations or try and solve for those variables in whatever way you can. Once you get it solved, it's just normal integration like we've been doing. All right, if you have any questions, please let me know. You all have a great day.